Well, hello everybody. Welcome to SVS404, a closer look at AWS Lambda. Hello everybody here in the room today as well. There's an overflow room somewhere in the broader things of Las Vegas, so hello to you there as well. And also if you're watching this in the recording, which is going to be posted on YouTube later, hello into the future. My name's Julian Wood. I'm a senior developer advocate here at AWS Serverless, work in a super cool team within the serverless organization, and I love helping developers and builders understand how best to build serverless applications and also be your voices internally to make sure we're building the best serverless products and features. And I'm going to be joined shortly by the awesome Chris Greenwood, one of our principal engineers in Lambda who works on the Lambda team. Now, this talk today follows on from two previous Lambda Under the Hood talks. The first at reInvent 2018, where Holly Misrobian and Mark Brooker first showed how some of Lambda works, where they covered the synchronous invoke path and introduced the Firecracker micro-VM technology. In 2019, they then covered how asynchronous invokes work, as well as how you could use Lambda to poll from Kinesis, and also about scaling up with provision concurrency. Well, today I'm going to start with a bit of a recap of how the different Lambda invoke models work, and then both Chris and I are going to dive deep into some of the interesting ways we've evolved the service since then and solved some interesting challenges to bring new functionality to Lambda. And you can use the QR codes, which use s12v.com, a link shortener for serverlessland.com, to watch the previous journey talks. Now, as a 400-level talk, we're not going to go into the basics of what Lambda is, but it is worth highlighting how Lambda is the fastest way to build modern applications with the lowest total cost of ownership. And we strive to help teams build more and faster by doing everything that makes cloud development hard. We make your distributed systems challenges Lambda's problems to solve. So teams can just focus on their code, which avoids all the maintenance costs and drudgery of making cloud software work. And as a bonus, costs align with the usage, which avoids a lot of waste from idle capacity. And Lambda really is the compression algorithm for experience. Turn code into a well-architected service with negligible operational effort. This is why serverless adoption is growing so fast. A serverless strategy enables you to focus on things that benefit your customers and not on infrastructure management. And we launched Lambda 8 years ago, and today more than 1 million customers have built applications that already drive more than 10 trillion Lambda invocations a month, and Lambda continues to grow at a phenomenal rate. We see customers building a wide range of applications with Lambda, but with a few common areas where they tend to see huge benefits. Maybe starting with IT automation, using Lambda functions to validate some config, maybe each time an EC2 instance is launched. Teams might then use Lambda integrations with something like S3 or with Kinesis streams or maybe Kafka to build data processing applications. Multiple teams may then start building whole microservices-based applications, often for web apps, and use Lambda with managed services as a critical part of their event-driven applications. And many customers are often using Lambda in machine learning applications. And we do a ton of innovation in all areas of the Lambda service to make the complex simple. Give you more while crucially keeping it simple to use, so you can take advantage of all Lambda offers to solve many challenges at any scale. And we think Lambda has been the pioneer in helping developers build serverless applications. From GA in 2015 through to support for 15-minute functions in 2018, provision concurrency and Event Bridge as a source in 2019, 2020 brought us container images and 10-gig functions, and Lambda extensions and ARM-based Graviton 2 in 2021, and this year, bigger temp-gig space and function URLs, all while adding more languages, shrinking latency, and improved integration with other services. For example, Coca-Cola, a great customer who had to react quickly to the changes brought on by the COVID pandemic. And they wanted to provide a touchless experience for their freestyle drink dispensers. And so they built a new smartphone app that allows customers to order and pay for drinks without coming into contact with their vending machines. Now, because they're built with Lambda, their team was able to focus on their application rather than having to spend lots of time on security, latency, or scalability, since with Lambda, well, that's all built in. And as a result, they built this new application in just 100 days, and now over 30,000 machines have the touchless capabilities. Now, one of the important benefits of Lambda is how it can respond to data in near real time. And as customers create more data streams, a serverless approach to processing data is super cool and appealing. And Nielsen Marketing Cloud is doing this at an incredibly high scale. They're using Lambda to process 250 billion events per day. Yes, that's with a B, all while maintaining quality, performance, and cost using a fully automated serverless pipeline. And the scale of the system is really why they actually opted for Lambda. On a peak day, Nielsen received 55 terabytes of data with 30 million Lambda invocations, and their system managed it with no problem. And they only had up to 3,000 concurrent invokes. Normal days, they've seen between 1 and 5 terabytes of data, and they were able to scale up to meet this additional need without additional work. Sure, their on-call engineers breathed a super sigh of relief. Now, while we're working on Lambda, we focus on things like availability and utilization and scale, security, and performance. And today, we're going to give you a taste of some of the engineering efforts in these areas. But we also have a priority list. The top priorities for Lambda are security, durability, availability, and then features in that specific order. And you may hear that that security is always job zero at AWS, and that's because it comes before everything else. After that, Lambda focuses on operational excellence for durability and availability, like running your functions in multiple availability zones to ensure that it's available to process events in the case of a service interruption in a single zone, and even in the unlikely event of an entire AZ outage. And we ensure that these basics are covered before we start working on new features. With security being job zero, we have the shared responsibility model, which has a separating line which defines how AWS is responsible for security of the cloud, the infrastructure and software that runs all our services, and your responsibility for security in the cloud to ensure that your applications and data are secure. But when building serverless applications, as with Lambda, AWS takes on even more of the security in the cloud. So you can worry less about things like operating system patching, firewall configuration, distributing certificates. You get to focus even more on your applications and data and let us manage the underlying platform. And a clear example of this was on December the 9th, 2021, when a seriously bad remote code vulnerability in Apache Log4j was announced to the world. Many companies were scrambling to update Java across their environments. Yikes, talk about ruining December for so many engineering teams. Maybe some of you are also in this room. But if you were using Lambda, we handled most of it for you. Now, Lambda doesn't include Log4j in its managed runtimes or base container images, so you were already protected. And if it had been included, you would be patched automatically. But we also worked with the Coretta team to build a mitigation. If you had Log4j as part of your function code, we could block the functionality and log that it had happened. Lambda protected you without you having to do anything. And one of the major technological foundations of Lambda is the open source Firecracker. Firecracker is a cool name. Firecracker provides superb resource utilization to run functions with enhanced security and workload isolation over traditional VMs with super fast startup times. Plenty more coming about Firecracker and how we're innovating in that space. So Lambda has two types of invocation models. Synchronous, caller calls Lambda either directly via the CLI or SDK, or using the newish function URLs, or maybe through a service like API Gateway, which is then mapped to a Lambda function. And this sends the request to the Lambda function, does its processing, waits for its response, and then returns that response back to the client. Now, when you invoke a function asynchronously, either via a client call or an S3 change notification, or a service like EventBridge sending an event when a rule is matched, you don't actually wait for the response from the function code. You hand off the event to Lambda, and Lambda handles the rest. It places the event in an internal queue and returns a success response to the caller saying, yep, I got your event. A separate process then reads the events from the internal queue and sends them onto your function. There's no direct path to the calling service. Now, also within Lambda, we've got these two different things. To do this, we have a number of different components. We've got a number of control plane components and data plane components, which I'm going to talk about. Now, also, just in case you're wondering, despite the rumors I hear, this talk isn't about how we've rebuilt Lambda to run on Kubernetes. Now, nothing against Kubernetes, but just in case you did wonder, we do not, in fact, run Lambda on Kubernetes. But the control plane services are where you interact with the Lambda service. You can create, configure, and update your Lambda function and upload your code to use the various services and features we expose. We manage the Lambda service resources too to make sure they're ready to handle any of your invokes. And there are a number of developer tools to interact with Lambda, which also cross over into some of the data plane tools. And this is from the console to the AWS CLI, SDK, some AWS tools for various IDEs, and also some other infrastructure as code tools. Now, the data plane responds to get the events to the Lambda service, and actually all invokes land up with synchronous with a number of internal services. Now, the eagle-eyed Lambda experts among you may have spotted a service we actually haven't talked about before, the assignment service. And we've been evolving the previous worker manager service, which I'm going to go into more depth later, on how we solved some worker manager problems and built the assignment service for improved availability. The async event invoke data plane with the Lambda polars then handle the very powerful asynchronous invoke model to process events and ultimately hand them over to the sync invoke data plane. So let's have a look at how a synchronous invoke works. Requests to invoke a certain Lambda function then arrive via the application load balancer, which distributes the invoke requests to a fleet of hosts, which run a stateless front-end invoke service. Now, as I said, Lambda is a multi-AZ service, so you don't have to worry about load balancing your functions across multiple AZs. Lambda just handles that for you. Now, I am simplifying the diagram a little bit here, or it does get a little crazy, but Lambda is built so all its components run transparently across multiple AZs. So the front-end invoke service first performs authentication and authorization of the request. So this ensures Lambda is secure as only authorized callers even get through Lambda's front door. The service loads the metadata associated with the request, and it's going to cache as much information as possible to give you the best performance. The front end then calls the counting service, and this checks whether any quota limits may need to be enforced based on account or burst or reserved concurrency. And then the counting service is optimized for super high throughput and sub 1.5 millisecond latency as it's called in each invocation, and it's critical to the invoke path, and like with much of Lambda, is made highly available across multiple AZs. The front end then talks to the assignment service, which has replaced the worker manager service, and it is stateful service, and there's going to be a lot of talk about state today. This is responsible, like the worker manager was, for routing invoke requests to available worker hosts, and the worker is the server in serverless. It's responsible for creating a secure execution environment within a micro VM to download, mount, and run your code. The worker is also responsible for managing the multiple runtimes, setting limits such as your memory based on your function config, and which also allocates then the proportional virtual CPU. And also, it's got a job to manage the agents on the host that monitor and operate the service. Now, here's also another component which does some coordination and manages some background tasks. This is the control plane service, which handles function creation and manages the lifecycle of assignment service nodes, and also ensures that the front-end service is actually up to date with which assignment node to send an invoke request. So, back to the assignment service. This is the coordinator, information retriever, and let's call it distributor about what state execution environments are on the worker host and where invokes should ultimately go. It also keeps the front-end service up to date with which assignment service nodes need to talk to. So for the first invoke of a function, a new execution environment needs to be started on a worker host. So the assignment service talks to the placement service to create an execution environment on a worker and gives it a time-based lease. Placement also uses ML models to work out where best to place an execution environment, maximizing packing density for better fleet utilization, while also maintaining good function performance and minimal cold path latency. And it also monitors worker health and makes a call when to maybe mark a worker as unhealthy. And also we need to make sure that this runs as fast as possible to reduce latency for any cold start invokes. So then once the execution environment is up and running, the assignment service gets your supplied IAM roles, and it's going to take that so the function runs with the privileges that you define and then distributes it to the worker along with the environment variables. The execution environment then starts the language runtime, so this is going to be Node, Java, Python, etc., and downloads the function code or runs the container image. And then the function init process runs. The assignment service then tells the front-end service, which sends the invoke payload to the execution environment. The function then runs the handler and then sends its result back through the front-end service to the original caller for the synchronous invoke. The worker then also tells the assignment service, yes, the invoke is now finished, so I am now ready for a subsequent warm invoke. So when a subsequent invoke does come in, front-end then checks the quotas with the counting service, and it also talks to the assignment service, which says, aha, yes, there is a warm and idle execution environment ready, and then sends the invoke payload to the execution environment on the worker, and your function runs the handler again. And the worker then tells the assignment service, I'm all done, I can now handle another invoke. Then when the lease of the execution environment is nearing its end time, the assignment service marks it as not available for future invokes. And there's then a further process within the execution environment to spin down those execution environments. Also, we need to check for errors. So if there are any errors in the init phase of the execution environment, also needs to mark it not available. And things need to also be refreshed. So sometimes when a worker needs to be removed from service, when it's ending its lease time, when it needs to be refreshed, or maybe it has errors, we can also gracefully drain it of execution environments by stopping future invokes, while the existing invokes can still carry on. So let's switch to talking about asynchronous invokes, or also what is called event invokes. Now you can see here we have the event invoke front-end service, and you may remember that for the sync invokes, we had a front-end invoke service, slightly different names. Well, the event invoke front-end service sits behind the same front-end load balancers as before, but now the load balancers actually see that it's an event invoke, and so send it to the event invoke front-end service, rather than the sync front-end service. Now, we actually deliberately separated these two services, building a new data plane to ensure that an async invoke path was separate to the sync invoke path to protect in case there's a large amount of event invokes, potentially causing latency for the sync invoke paths. Just another way we could improve availability and performance on your behalf. Now, I'm also simplifying the diagram a bit here compared to the sync invoke, but again, all of this is spread across multiple availability zones. The service then is going to do authorization and authentication of the request based on who the caller is. So the front end then sends the invoke request to an internal SQS queue and responds with an acknowledgement to the caller, as I said before, that Lambda is going to invoke the function asynchronously. Now, Lambda behind the scenes is just going to manage these SQS queues, and you don't really have any visibility of them. And we run a number of queues, and we dynamically scale them up and down depending on load and function concurrency. Now, some of the queues are shared, but we also send some events to dedicated queues, and we do this to ensure Lambda can handle a large number of async invokes with as little latency as possible. We then have a fleet of Polar instances which we manage. And an event invoke Polar needs to read the messages from the internal SQS queue to determine the account and the function and get the payload. And then it sends the invoke request synchronously to the sync front-end invoke service. As you can see, all Lambda invokes ultimately land up as synchronous. The function then uses the same sync pathway I talked about before and then runs the invoke. The sync front-end returns a function response to the event Polar, which can then delete the message from the queue. And if the response is not successful, the Polar returns the message to the queue. And this actually uses the same visibility timeout as you would with your own SQS queues. So the same, or maybe another Polar then picks up the message and will try again. You can also configure event destinations for async invokes to provide callbacks after processing. So whether the invokes are successful or they failed after any retries are exhausted. So there are also some control plane services involved. The queue manager, that looks after the queues. It's going to monitor them for any backups, and then also does the creation and then deletion of any of the queues. And then it also works with the leasing service, and this manages which polars are processing which queues. And it also detects when maybe a polar is going to fail, and so it can grab the work from the failed polar and pass it on to another polar. Now, when we built the Lambda async model, we realized, well, this idea could be used for a number of other service integrations. So an event source mapping is a Lambda polar resource that reads items from a source. Now, initially, this was only for Kinesis or DynamoDB, but we've expanded this to pull from your own SQS queues. Kafka sources, including your own self-hosted Kafka. I mean, yeah, that's not even an AWS service, as well as Amazon MQ for Rabbit and ActiveMQ. And the pollers pull messages from these sources. They can optionally filter them, batch them, and then send them to your Lambda function for processing. So let's look a bit more detail how this works. So a producer application puts messages or records onto the stream or queue asynchronously. Then we then run a number of slightly different polar fleets because the polars have different clients depending on the event source. So the polars then read the messages from the stream or queue and can optionally filter them. This is a super useful functionality just built right into the system. It helps reduce traffic to your functions, simplifies code, and reduces overall cost. It then batches a whole bunch of records together, which you configure into a single payload, and sends it to their function synchronously via the same invoke front-end service. Again, all Lambda invokes eventually land up being synchronous. Then for queues, the polar can delete the message from the queue when your function has successfully processed them. And for Kinesis and Dynamo, you can also send information about the invoke to SNS or SQS. Now, again, we manage these polars for you as part of the Lambda service, which is a huge benefit. You don't actually have to run your own consumer EC2 instances or have a fleet of containers just to poll for messages, and it's actually free. You don't even pay extra above your function invokes for the service. It's just more and an example of what Lambda can do for you. There are also some other control plane services over here. We have the state manager or stream tracker, and that depends on the event source. And this does a similar thing for async. It manages the polars and the event sources, discovers what work there is to do, and handles scaling the polar fleets. The leasing service then assigns polars to work on a specific event or a streaming source. And again, if there are any problems with the polar, it can move its work to another polar. And so all of this functionality and having these polar fleets allows us to support a huge number of event source features. Now, I mean, there's a lot here, but think of it, we can do filtering, we can configure batch sizes and windows, and reporting on partial batch failures, and like a whole raft of settings depending on the event source. And you configure these on the event source mapping itself, or sometimes on the source, but it really makes it easier to process data at scale with Lambda. So that covers the sync, async, and polar functionality that works with Lambda. Now let me hand you over to one of our top Lambda gurus, Chris Greenwood.
Thanks, Julian. My goal here today is to demonstrate that in some ways, Lambda is a storage service. My first position with AWS was working on Elastic Block Store, or EBS. EBS is a large distributed storage service that backs the majority of EC2-attached block devices in the world today. The service is faced with many of the traditional state management challenges that you may have heard about in some of the talks from the storage track. A few years ago, I joined Lambda expecting to find many different challenges, more serverless, more ephemeral, more stateless. But in fact, what I found was that many of the problems that I faced in EBS around state management, I also faced in Lambda around state management. What I came to realize is that Lambda is a stateless, serverless compute product to you, the function developer, but on the back end requires solving many of the same state management challenges that are present in a storage service. To some degree, Lambda is a storage service that you don't have to think about. So for the next segment of this talk, I'd like to look at Lambda as a storage service. And we're going to focus on 3 different lessons that Lambda has learned from our peers in the storage services that have helped us improve the Lambda service. Lesson 1 is that access patterns to your data should drive the storage layout of that data in your data plane. Lesson number 2 is that shared state is super important for optimizing the performance and the utilization of a storage service, and that the best kinds of shared state are those where you actually don't take shared resources as a dependency. And then lesson 3 is that a well-architected storage service often involves a well-architected presentation layer into your caller. You meet the caller where they are. We're going to start with lesson 1. So to frame the topic, what state needs to be managed by the service in order for Lambda to serve an invoke? Fundamentally, an invoke requires 3 things. First, it requires invoke input. This is the JSON payload provided by the caller or provided by the event source on every invoke. Second, it requires function code. Function code is provided by the developer when creating or updating a function. And third, it requires a place for function input and for function code to meet the virtual machine. That's 2 pieces of state and 1 piece of state and compute in the virtual machine, that together form the necessary bits of information to serve and invoke. Julian gave an overview of front-end invoke and pollers that together serve to get the invoke input from the outside world to the correct machine at the correct time. Now we're going to focus on code. So when Lambda launched, to deliver code to a machine in order to start up an execution environment, Lambda did the simple thing. We downloaded the code from S3. Each execution environment would start up with a small amount of Lambda service code that would discover the code payload that governs a function, would download that code payload from S3, would unpack it into the runtime, would start the runtime, and would execute the function. This basically turned a code payload into a running VM, and that running VM would then be able to accept invoke input and execute. This worked fine, and is in fact the way that the majority of Lambda functions work today. But as our requirements changed, so did our architecture. In 2020, we set out to build container package support for Lambda. This changed state management in a big way in that code payloads were now much larger. While zip code payloads are limited to 250 megabytes in size, container payloads are often much larger than 250 megabytes, and we decided to support up to 10 gigabytes in size for a Lambda function defined with a container image. This changed the state management problem in a big way in that code payloads were now much larger. But the code delivery architecture for Lambda made it such that the time to deliver a code payload into the execution environment scaled linearly with code size. And we felt this was unacceptable for our new code payload requirements. So really what this meant was we had to rethink the mechanism by which we delivered code into the execution environment. We, along with the community, realized something. In many containerized workloads, the application reads a subset of the container image when actually serving a request. This chart from a harder paper published in the FAST conference in 2016 shows the disparity between total container image size, either compressed or uncompressed, and the total amount of that data read by the container when serving a request. While the mechanism Lambda uses to leverage this ends up being different than that of the harder paper, we realized that if we could download and present to the execution environment only the bits of the container that are necessary to serve a request, we could get an execution environment serving the request much more quickly, and we could amortize code delivery over more requests. So, how to go from all-at-once code delivery to incremental code delivery? We first had to change the storage layout for Lambda container images. This is what a simple Docker file may look like for a container image holding a Node.js function. When you build a container image from a Docker file, Docker is going to produce a set of tar files called layers. Lambda takes those layers and flattens them into a file system. This is the file system that your execution environment perceives when it starts up. Once we have the flattened file system, we break its binary representation on the block device into chunks. A chunk is a small piece of data that represents one logical range of the block device, and multiple chunks appended together make up the entire block device and the entire file system. Chunking is powerful because it lets us store contents at a sub-image granularity and then access those contents at a sub-image granularity. Let's consider an example here of a file system presented into the execution environment. When the execution environment starts, it knows nothing of the contents of the file system. First access of the file system, say to list the contents of root, results in an inode read to the file system. Lambda software maps that inode to a particular chunk of the image and fetches this chunk to serve the read. A subsequent read to a different inode, say to open and start and execute the Java binary, may fall to the same chunk, meaning no additional contents need to be loaded in serving that inode read. Future reads, such as opening the handler class file, may fall into different chunks, and chunks are loaded only as they are needed. This means that all up, Lambda delivers to the environment the contents needed to serve the request the VM is making against the file system, and does not deliver contents that are not needed. In this way, Lambda has learned lesson one. We use the understanding of customer access patterns, specifically the fact that container images are generally sparsely accessed, to drive the layout of code storage in our data plane for efficiency and for performance. Moving to lesson 2, sharing state without sharing state. The next thing we realized about container images is that they often share content with similar images. This is for the simple reason that when people build with containers, they often don't start from scratch. They use base layers. A customer of Lambda may start with the base OS layer, lay on top of that the Lambda-vended Java runtime, and finally lay on top of that their function code. The Lambda data plane understanding which data is shared and which data is unique is helpful in optimizing code delivery. But it turns out that deduplication is difficult in this context for 2 reasons. The first is related to the fact that our storage layer is block-based instead of file-based. To allow 2 copies of the same file system state to share contents at the block level, they must deterministically flatten layers onto the file system, and they must deterministically serialize that file system onto the block device. But many file systems don't do this. In some file systems, if you take the same set of layers multiple times, flatten them onto file systems, and then serialize those file systems onto disk, you get different representations on disk, which breaks deduplication. To solve this, we did some work in the ext4 file system to ensure deterministic flattening and deterministic serialization for Lambda. The second reason deduplication is hard is related to key management. We need different keys encrypting different customers' unique payloads in different regions. But different keys mean different encrypted payloads even for the same contents. And different encrypted payloads means that you can't deduplicate. So ultimately, to benefit from deduplication, we need certain contents, the contents that can safely be done so, to share keys so that they have the same encrypted payloads. A simple way to do that would be to keep a shared key in a shared key store. But that results in a single point of scaling across multiple customers and across multiple resources. What we want is for the keys to logically be the same, but for the discovery of and persistence of the shared key to be pushed out closer to where the data itself is stored. To solve this problem, we turn to a technique called convergent encryption. When encrypting a chunked image, we start with a plain text chunk, which represents one segment of the flattened file system. We then append some extra data that is deterministically generated by the Lambda service. We then compute the hash of this chunk and extra. That hash becomes a unique per chunk key. This key is used to encrypt both the chunk and the extra data. This creates an encrypted chunk including the extra data in the encrypted chunk is helpful because on the decryption path, we can ensure that the deterministically generated extra data matches what we expect, ensuring that the encrypted payload has not been modified either at rest or in flight. We do this for each chunk in the file system, writing encrypted chunks in our chunk store and keeping track of the keys for each. When complete, we create a manifest containing both the keys and pointers to chunk contents in the chunk store. We finally encrypt the manifest with the customer-specific KMS key and persist the manifest. There are a few great things about this encryption scheme. First, assuming we use the same extra data, we produce the same encrypted data from the same contents every time. This allows us to securely deduplicate contents that should be deduplicated. And critically, this allows us to deduplicate while having each image creation process proceed independently without depending on a shared key. Second, without changing the encryption scheme, we can simply change the extra data appended at the end to force 2 chunks to use different encryption keys, even if their contents are the same. This is helpful in ensuring, for instance, that contents in different AWS regions use different encryption keys, even if they're identical. So in this way, Lambda has learned lesson 2. We improve cache performance and economics to help the overall performance of the system, all while minimizing the shared resources on which we take a dependency. So to recap, we have covered invoke input delivery and code payload delivery. The third aspect of state management we're going to talk about is the place where code and input meet, the VM. A quick recap of Lambda's history with virtualization architectures. Lambda operates a large fleet of EC2 hardware dedicated to running the millions of active functions in a region. At launch of the service, Lambda provisioned T2 instances on that hardware and dedicated a T2 instance to each tenant to run one or more of that tenant's execution environments. This leveraged EC2 virtualization to isolate one tenant from another. Simple and secure. When a request was handled by the routing layer, it would check for an existing execution environment, and if one did not exist, it would initialize a T2 instance with the information necessary to download the code and execute the function. At scale, this meant many occupied instances in the fleet at any given moment in time, and many instances in the process of being brought into service for a function or brought out of service for recycle to a different function. And this brings us back to state management, but from a different angle. While with code management, our goal was to scale up the amount of state managed, with our VM fleet, our goal was to scale down the amount of state managed, provisioning as little unnecessary compute, memory, and disk resources, reducing the overheads of a function. Reducing overheads is good for efficiency, both the efficiency of the fleet at rest and the efficiency with which we scale the fleet up and scale the fleet down. This need to scale down our virtualization technology led to the introduction of Firecracker micro-VMs into the Lambda architecture in 2018. Firecracker is a virtual machine manager that Lambda runs on bare metal worker instances. It uses Linux's KVM to manage hundreds or thousands of micro-VMs on each worker. This allows Lambda to benefit from multi-tenant worker instances while using secure VM isolation between tenants. Firecracker handles I/O between the micro-VM guest kernel and the underlying host kernel. Within each micro-VM is the execution environment you're used to, including the runtime, function code, and any configured extensions. Firecracker allowed Lambda to both scale down and right-size while maintaining the secure VM boundary between environments. Instead of allocating an entire T2 instance to each environment, we were able to allocate a much smaller VM, potentially from an existing instance, to each execution environment. Less overhead per VM made the VM fleet more efficient and also made the operations of standing up a VM or recycling a discarded one more efficient. This move to Firecracker as a virtualization technology allowed us to leverage lesson number 3, meeting our caller where they are. So now in our high-level architecture, we have our chunked, encrypted images, and we have the micro-VM that intends to make use of those images. But we need to expose a usable container image or file system into the micro-VM. And in this regard, our job was a little bit harder with container support than it was for zip packaging. Let's focus in on a single micro-VM on a single host. With zip packaging, since Lambda owns and manages the runtime, we're able to employ a small amount of code in the VM that knows what to do with the code payload to start the execution environment. But with container packaging, the whole concept is that the entire guest environment is customer provided, leaving nowhere in the guest to implement image handling functionality, such as fetching from a chunk store, encryption, and so on. With our EC2 virtualization stack, this would have been the end of the road, as running in the guest was our only option. We were, in fact, the guest of EC2. But running Firecracker on bare metal, we had space to securely run service code outside of the customer VM. So we built a virtual file system driver that presented an ext4 file system from the worker into the VM. When the VM issues requests against the file system, they are handled by Lambda code outside the VM. Our file system implementation interprets the manifest to deterministically map inode reads coming out of the VM to chunk accesses in the image. It interacts with KMS To securely decrypt the manifest, it caches chunk metadata, and it serves file system writes from a local overlay inside the file system. In serving reads, the file system consults various tiers of cache, from a host local cache to a larger in-AZ cache to the authoritative chunk store in S3. All of this chunking, decryption, and cache tiering work is abstracted from the customer or from the execution environment behind a simple, ubiquitous file system interface. In other words, we meet the caller where they are, abstracting away the complexity of a storage subsystem. This mostly completes our storage journey, from management of invoke input, to management of code and container images, to the presentation of code into the VM. However, we realized an additional opportunity to leverage all of this state management work and all of these lessons learned to meet the evolving needs of our customers. So let's talk about the elephant in the room when it comes to Lambda outlier latencies: cold starts. Over 99% of invokes to Lambda are served by an execution environment that was already in service when the invoke was made. These are warm starts. But occasionally, due to idleness or due to scaling up of incoming calls, an invoke must spin up a new execution environment to serve the invoke. This is a cold start, and it can significantly impact a function's outlier latencies. Spinning up a new execution environment involves steps like launching the VM, downloading code, unpacking code, and critically includes the steps of starting the runtime and executing function initialization code. These steps of starting the runtime and initializing the function can dominate cold start time, especially for languages like Java with a language virtual machine that needs to start up. And this time and cost must be paid on every execution environment that is brought into service for your function. So while cold starts can be rare, they can also be impactful to the customer experience. At Lambda, we track our control plane and our invoke latencies at a P99 level, P99.9 level, and above. Outliers are rare, but have an outsized impact on customer experience, so outliers matter to service owners. Thinking about the initialization process in the abstract, what this process effectively does is it takes code presented into the VM, and it turns that code into a running VM that is then ready to serve an invoke. So to solve this problem of reducing initialization times, what if we could use the storage lessons learned by Lambda to avoid the conversion process of converting code to a running VM completely? To do so, what if instead we could deliver we could deliver a different artifact, an actual running VM, to the host instead? This is what we're doing with Lambda SnapStart. SnapStart automates the management of execution environment snapshots to significantly improve the outlier latency of Lambda functions. SnapStart is initially available for the Corretto Java 11 runtime, and it is powered by the open source work in the Firecracker project supporting micro-VM snapshot and restore. With SnapStart, the lifecycle of an execution environment is different. When you update your function code or configuration and publish a new version, Lambda will asynchronously create the execution environment, download code and config, and initialize the function up to a point where it's ready to serve an invoke. And critically, no invoke has happened yet. Lambda will then take a VM snapshot, chunk it, encrypt it, and persist the resulting manifest and chunk contents. Then, on the invoke path, if a new execution environment is needed, Lambda will restore a new micro VM from that persisted snapshot. After a short restore phase, the execution environment is ready to serve traffic. The net result of the application is that long-tail latencies can be drastically reduced, in many cases by up to 90%. You might notice one application in this suite that actually did not initially get much benefit from enabling SnapStart. Upon making a few minor code changes, however, it achieved the largest speedup of the application sampled. Most functions will see significant outlier latency improvement with only the configuration change, but occasionally a function may need simple code changes to benefit. As with all performance features in AWS, try it out and let us know how it goes. And this improvement to cold start experience was made possible by turning a compute problem, converting code into a running VM, into a storage problem, delivering a running VM onto the host. So in summary, Lambda has employed a few lessons learned by our storage service peers to improve the performance, efficiency, and overall experience of the service. Lesson 1 is that we use access patterns to our data to drive the storage layout of the data in our data plane. Lesson 2 is that shared state is super important for performance and for efficiency of a storage system, and that the best kind of shared state comes without shared resources. And lesson 3 is that a storage service spends a lot of time meeting their caller where they are to hide the complexities inherent in a storage service from the customer. I'm now going to invite Julian back to the stage for the last segment of the talk. Thanks.
Thank you, Chris. Is my microphone on? Yes, thank you. Well, anyone happy that we've solved Lambda cold starts with some pretty cool technology for Java just behind the scenes so you don't have to do anything? Anybody happy? Oh, we've got a few happy people. That's good to know. Thank you. Chris and his good, excellent engineering work. Well, Chris has been talking a lot about state and how we've used lessons from storage to solve moving some pretty heavy workloads around, big stateful workloads to support container images and ultimately snapstart. But we also have state to deal with elsewhere in Lambda. Yes, a little bit behind the scenes, but important in also getting that invoke payload to the execution environment. So remember I said earlier we previously had the worker manager, which was the coordinator between the front-end invoke service and the worker. Well, it had a super important job to help the front end get the invokes to an execution environment and then also manage the execution environment lifecycle. Well, we had an issue. It's one of the first parts of Lambda and, to be honest, getting a little bloated. Each worker manager stored a list of execution environments it was responsible for on which hosts. Turning it the other way around, the state of any individual execution environment was known to exactly one worker manager instance, which stored it in memory. Now, this was nice and super fast, but stateful and not replicated, no redundancy. We had a problem with state with worker manager. So in this example, a worker manager in purple, if you can see the different color, manages a whole bunch of purple execution environments on a number of worker hosts. And we did have a control plane service to manage the worker managers. If the worker manager fails, all those execution environments it was looking for after are orphaned. Excuse me. They continue to handle their existing invokes, but for any new invokes, the front end has to ask other worker managers for an available execution environment. But other worker managers don't know about the existing warm execution environments, and so the placement service has to create new ones. And that's a bad customer experience of a cold start when there's actually a warm execution environment available, but it's orphaned. And this also means we have to have more spare capacity in the Lambda service to run these additional execution environments until we can reap the orphaned ones, which we do in time, but this impacts how efficiently we can run Lambda. And the issue gets even worse when you think about how Lambda distributes traffic across multiple AZs, particularly for smaller regions. Here we have an execution environment in AZ1 that's actually owned by a worker manager in AZ2. If we have a zonal failure in AZ2, which is extremely rare, but we do need to plan for, all worker managers fail in AZ2 along with all execution environments on those worker hosts, so that's a third of execution environment capacity in a region gone. Yet, as there are execution environments in AZ1 and 3 that are registered to that worker manager in AZ2, all those execution environments, although up and running and not impacted by the zonal issue, also become orphaned. So that works out to 1/3 unavailability within each of the 2 other AZs. And that comes up to like a combined total of 55% of execution environment capacity unavailable. Now, of course, we hold spare capacity in Lambda to handle this sort of failure, but this means a huge capacity buffer and a poor customer experience, as each execution environment that needs recreating means a cold start. And this also means the placement service needs to be scaled enough to handle this huge increase in additional requests. And so we decided that Worker Manager needed a refresh, and we built the assignment service. Instead of a single Worker Manager in a single AZ managing a set of execution environments across multiple AZs, we built the assignment service made up of 3-node partitions split across AZs. Looking at this logically, a single partition consists of 1 leader and 2 followers, each in different AZs. And we can run many partitions depending on load, and each assignment service node can host multiple partitions. The assignment service partition members use an external journal log service to replicate execution environment data. The leader writes to the journal, and the followers read the log stream from the journal to keep up to date with the assignments. And the partition members can then also use this log journal approach to elect the leader. So the front end talks to the leader, and the leader communicates with the placement service to create new execution environments, and then keeps track of the assignments on the workers, and then writes this info to the log, which the followers then read. If the leader fails, a follower can take over really quickly, and we don't lose the state of which execution environments are available to service subsequent invokes. And this means in a zonal outage, execution environments in the working AZs are not orphaned, which means fewer cold starts, less idle capacity needed, and less load on the placement service. It also means the assignment service has much better static stability. The system maintains stability and state itself. We don't need an external service to fail over functionality to keep the system running and servicing invokes. And good static stability is something we are always working towards in AWS and Lambda, a good way to maintain state. So when we then do need to bring up a replacement follower, or when we need to add and remove assignment service nodes for maintaining the system, we can bootstrap the state of all assignments owned by the partition by reading from the journal log stream from the time of the oldest execution environment to quickly get up to date. And we do still have an assignment service control plane which manages creating the partitions and ensures the front end knows which partition to talk to for a particular function on. So the assignment service is fully resilient against host, network, and even AZ failures, using a partitioned leader-follower approach. And we also managed to slim down the service by moving some of the functionality elsewhere. And it's also written in Rust for performance, tail latency, and memory safety. And altogether triples the number of transactions per second we can run on a host with a meaningful reduction in latency. So all the efficiencies we're able to drive in the service means we can get better utilization. And this has a direct impact on the cost of running Lambda. How efficiently we can run a workload given a set of resources, and we do a ton of work in this area. Due to the small footprint of functions and our ability to distribute the workload to fit the curve of our resources, we can be the most efficient way to run code. With Lambda, you only pay when your functions are doing useful work, not the idle. It's our job to minimize the idle. So inside Lambda, we optimize to keep servers busy and reuse as much as possible. And we are continually optimizing the worker utilization to be more efficient running Lambda and also improve your function performance. So here we have systems that help us. We also have systems that help us analyze the resources needed over time so we can optimally distribute workloads and provision the capacity to fit the curve. So for a given function in an execution environment, you may think, well, distributing that load evenly is the best way, but it actually means you miss out on efficiencies. Things like cache locality, which you've heard about, is super important, and the ability to auto-scale. And so it's actually better to have some concentration of load, but within reason. The worst for efficiency is actually a single workload on a server. It's then got a specific pattern and is inefficient with resource usage. So it's better to pack many different workloads together so workloads are not as correlated. But we take this a step further. We use models and machine learning to pack workloads optimally together to minimize contention and maximize usage while securely caching the common data across different functions, which also improves the aggregate performance. And we actually have an entire team that works just on this placement problem with a distinguished professor and a whole team of research scientists. And this is all part of the story of how we built Lambda to be the best place to run workloads in the cloud, handling as much of the hard distributed computing problems, especially with state, so you can have the fastest way to build modern applications with the lowest total cost of ownership. So to continue AWS learning, use the QR code to find more information to learn at your own pace, to increase your knowledge and even earn a serverless badge if that's your thing. Now, for plenty more general serverless information, head over to serverlessland.com with lots of resources, everything about serverless on AWS. But most importantly, thank you so much for taking the time today. Chris and I really appreciate you coming late on a Tuesday when there's other things to go to learn a little bit more about Lambda. And we hope we were able to educate you and teach you a little bit about all the stuff we do from Lambda under the hood.